And now, please welcome to the stage, Sandy Irani.
Hello, good morning, and welcome to day 3 of QIP. Our first speaker this morning is Ewin Tang, and she's going to tell us about high-temperature Gibbs states, are unentangled and efficiently preparable, and here she is.
Okay, great. Thanks for having me. So I'm going to be talking about this work, which is joint with Ainesh, Alan, and Ankur. I think Alan should be here today, so if you have any questions, you can ask him or me. Also, we have a new archive preprint, which should have sort of improved exposition in case you're curious. Okay. So this work sort of sits at the intersection of these two different fields. On the one hand, we have statistical mechanics, which is asking sort of for physical systems, how do macroscopic phenomena emerge from like local interactions and sort of the strengths of local interactions? And on the other hand, we have quantum information, which is sort of this field that's developed recently that is all about entanglement, how we can sort of understand, harness, and sort of measure the amount of entanglement in these systems, in physical systems. And so it's a sort of natural question at the intersection of these fields of whether entanglement can exist at any temperature. So our work answers this question, and in the negative. So we prove this result about heat-destroying entanglement. What we show is that if you take a Gibbs state of a local Hamiltonian, it's going to have 0 entanglement above a constant temperature. So Gibbs states of local Hamiltonians, this is the standard way to model a sort of locally interacting system at thermal equilibrium. If you have a system at thermal equilibrium, this is typically modeled with this unique thing known as a Gibbs state. And interestingly, our proof for this structural claim goes through an algorithm. So I'll be describing this algorithm moving forward. And sort of the algorithm is going to construct some proof that our Gibbs states are unentangled. Okay, so just to give some more context about this like statistical mechanics sort of connection, one common thing that you like to do in these sorts of domains is that you look at Hamiltonians and then you look at their Gibbs states. And then you look at correlation functions on these Gibbs states. And what you can see is that there's some like phase transition phenomenon where for low temperature, here beta is a parameter that corresponds to the inverse temperature. So in this convention, like beta being infinity is absolute 0 and beta being equal to 0 is infinite temperature. So it's going from, I guess, cold to hot. And these Gibbs states, they start off very correlated at low temperatures. And then there's a phase transition, and they become very uncorrelated. They have some correlation decay at high temperatures. Now, the interesting thing here is that these classical correlations in these classical Gibbs states, they always exist at any temperature. So there's always going to be some amount of correlation in these Gibbs states. Our work shows that if you look at quantum correlation, aka entanglement, for quantum Gibbs states, the story is a bit different. So the situation for quantum Gibbs states is that the quantum correlation starts off, being potentially large, but there is some temperature at which your entanglement reaches literally 0, and it stays there for, that temperature and above. And so this is some like notable difference between the behavior of quantum entanglement and sort of classical correlations. Okay, so for this talk, I'm going to be doing so for the outline for the talk, I'm going to first of all describe this formal statement. It'll be a bit of like technical stuff, just to get it out of the way. And then I will start off by discussing the broader context and sort of building up to our proof ideas. And then I'll discuss sort of all of the results that we get and do some discussion from there. Okay, so first of all, this defining all of these things that I've been using so far. So for the Hamiltonian class that we're considering, we're imagining geometrically local Hamiltonians. So we're imagining that we have some number of qubits, n qubits, and this is on some lattice in constant dimension. Here it's 2. And so all of our operators that we're going to be working with are in the space of C2 to 2 to the n by 2 to the n, this tensored space of n qubits. And the class of Hamiltonians is going to be things that look like, for example, this like classical Ising model. This Hamiltonian is an operator, and it's this sum of local operators in the sense that there are these individual terms which act on it's a sum of these terms, and these terms act on sort of edges of this lattice. And these sort of terms are sort of local in that sense. And so the formal thing that we say is that we're considering a local Hamiltonian to be like a sum of these terms, sum of m terms, where the operator norm of these terms is bounded, and each term is supported on like a vertex or an edge. And we have some like linear number of terms. And just by expanding every Hamiltonian term into the Pauli basis, we can assume without loss of generality that these Hamiltonian terms in fact take the form of lambda times p, so like a rescaled Pauli, or tensor product of Paulis. So if you want, you can actually think of like, oh, like this classical Ising model, but maybe replace these sigma z's with your favorite choice of Pauli. Okay, so that's the class of Hamiltonians that we're going to be considering. As for the Gibbs states, this is what I mentioned this state at thermal equilibrium is. We define it for a particular inverse temperature beta to have the density matrix proportional to e to the minus beta h. And so remember that beta is sort of on the sliding scale, and we can imagine that this Gibbs state as a function of temperature. At beta equals 0, you can see that this exponential e to the minus beta h just becomes the identity. And so the corresponding Gibbs state is the maximally mixed state. On the other end of the spectrum, we have beta going to infinity, and then our state is going to be proportional to the ground state. And so you get these sort of, typically in these settings, you have sort of 2 regimes, this high temperature and low temperature. And at the high temperature, your Gibbs state sort of looks mixed, and at the low temperature setting, your state sort of looks like the ground state, something like that. Okay. As for unentanglement, a Gibbs state is unentangled. I'm also going to call it separable. If you can prepare it without using quantum correlations, in the sense that you don't need to prepare it with quantum operations on multiple qubits at a time. So for example, if I have like this 4-qubit system, I can imagine preparing a state by like applying a qubit at a time, by preparing 1 qubit at a time. So I prepare my first qubit, second qubit, third qubit, and so on. And because I'm doing this sort of individually, the states that I'm getting are unentangled. But as soon as I apply a quantum gate to like 2 qubits at a time, I could generate entanglement. And so this is like an operational definition of what separability is. There's a corresponding mathematical definition, which is that a state is unentangled if you can write it as a convex combination of product states. So this is a convex hull, pretend it's convex. And you're imagining that my state is unentangled if I can write it as like some distribution over these product states, which for like n equals 2 look like something like this. The normalization is going to be something that I'm just going to ignore, because actually for unentanglement, it doesn't really matter. You can define unentanglement for unnormalized states as well. So you can just consider a general operator, and you can say that it's unentangled if you can write it as a sum of these unnormalized product states. So before it was a convex hull, now it's the cone of product states. And so this operator is unentangled if we can write it in this way, where it's this sum of product operators, where all of these product operators are PSC. And all of these definitions so far are consistent. And so just to emphasize what I'm going to be doing, we're going to be proving that these operators are separable by decomposing matrices into the sum of products. But equivalently, I'm going to be using this algorithmic understanding of what's going on where if I have, where I can prove that an operator is separable if I can sample some random product state, or product operator, whose expectation is proportional to x. So you can see that if I just sample a random a from the sum of this decomposition that I wrote above, then this thing is actually going to be proportional to x. And moreover, because unentanglement doesn't really care about the normalization, you know, if you multiply a scalar, it's still going to be unentangled. Then this shows separability for x. Okay. Now, with all this said, our formal result is that if you give, if I'm considering a Gibbs state of this local Hamiltonian from our specified class, this is going to be separable at inverse temperatures below a constant. So there's some constant critical temperature below which our Gibbs states are unentangled. And so one thing this shows in particular is that entanglement has this critical temperature. So there's this point that I sort of showed in this previous diagram where your entanglement hits 0 as you increase the temperature. And yeah, so our work shows that this critical temperature is a constant. It's at least a constant. And in case you're curious, you can try to prove that it's greater than 0. I'll get back to the proof of this, but you know, just something to test your intuition. So this fact that the critical temperature is greater than 0 is giving us a sudden death of thermal entanglement, which is what I said before, where our entanglement actually hits 0 before infinity, as opposed to classical correlations, which do not. Okay, so if you are familiar with some of the broader context, you might be wondering why nobody's ever proved this before, sort of what's the state of the literature, because there are a lot of works about correlations in quantum Gibbs states. And so I want to sort of elaborate on what's going on there. And the interesting thing is that like prior work doesn't really tell us about this critical temperature. I'll discuss these two bodies of literature. First of all, this correlations of quantum systems literature that you might see at QIP. And then I'll go back a little bit further and talk about some older computational evidence. So, you know, as I mentioned, there's a lot of literature about entanglement in Gibbs states. There's all these kinds of literature. There's this great survey by Alvaro discussing all these in detail. But what these do is they try to understand, like, if I look at quantum Gibbs states, can I prove things about how little entanglement there is between regions? And so you might wonder, like, okay, does this stuff say anything about this critical temperature? It turns out that all of these are bounding quantum plus classical correlations. So they're bounding entanglement, but they're bounding it by this proxy of just correlations in general, classical plus quantum. And the thing is that classical correlations exist at all temperatures. So you're never going to see from these bounds that the entanglement actually drops to literally 0. And so these works don't actually give bounds on, don't actually say that there's a sudden death of thermal entanglement. So you might even like, from this literature, you might even like not even expect that this statement about entanglement is true. There's another literature where this is maybe a bit more believable, where people look at quantum Gibbs states and they try to simulate them on their computers and try to understand, like, plot sort of entanglement metrics and try to understand the behavior with various parameters. So you can see that there's this diagram of like this kind of entanglement with temperature in this particular model, and you can see that at some particular temperature you hit like actually 0. And there's another work which does this thing for this other kind of entanglement metric. So, but the interesting thing here is that these graphs are not showing entanglement. They're showing an entanglement proxy. And so these entanglement proxies are sort of, well, proxies for entanglement. But interestingly, these quantities can be 0 even for entangled states. Okay? So, you know, even though we do see this like sudden death of thermal entanglement in these sort of graphs, it's not exactly clear whether this actually means that you should see genuinely 0 entanglement at these temperatures where your graph says you're 0. Okay. So overall, there's this literature, all this literature that sort of doesn't quite give you the right statements about this beta critical. And there's this broader barrier that exists here, which is that determining whether states are separable is really complicated. Basically, there's been a lot of work on this sort of thing from the quantum information perspective. But basically, this definition of separability doesn't really have a nice operational definition. It's hard to detect entanglement. It's hard to optimize over the space of separable states. So generally, this thing is hard to work with. And I think that's sort of these sorts of difficulties are reflected in the literature where you don't see that much work on this. OK, so we're able to prove that some Gibbs states are unentangled. How do we do this? Well, the first thing we should ask is why is anything unentangled? We're going to give a simple argument that we have this sudden death. And we're going to bootstrap this to some stronger intuition about when things are unentangled. OK, so I was being a bit misleading when I just was discussing literature earlier. There is one work, or one series of works that will be useful for us for proving sudden death of thermal entanglement. And that is this work that says that if you take a maximally mixed state and you perturb it, you're still separable. So I'm going to continue discussing the unnormalized states here. So I'm considering the identity operator, maximally mixed. This thing is separable because you can write it as the tensor product of identities. But also, if you perturb the identity, you're still going to be separable. So the thing that you can prove is that if I take the identity and I perturb it by some operator, it's going to be separable provided the operator norm of that thing is exponentially small in the number of qubits. Basically, what this means is that sort of any small amount of perturbation it can be modeled by classical correlations or something like that. And so with this, we can then go back to that question that I asked before and show that your beta critical is greater than 0. The way to do this is by this simple geometric argument. I consider my Gibbs state, rho beta, at infinite temperature, beta equals 0. So this is going to be the maximally mixed state. And so in particular, it's separable. But we also know from the previous discussion that it's in the interior of this space of separable states. So it's separable, and also every perturbation is separable. So it's it's separated from the outside by some radius. And furthermore, your Gibbs state is going to be some continuous function of beta. So I can smoothly change beta, and my Gibbs state, rho beta, also changes smoothly. And so there is going to be some beta greater than 0 for which my Gibbs state is separable. This is a continuity argument. And if you want a quantitative bound, we know that this radius is going to be exponentially small because of the thing that I said before. And the sort of right amount of continuity that you need gives you that your beta critical is something exponentially small in n. OK, so this is good. This tells us that at temperatures which are exponentially high in system size, you do get a separable state. However, we're shooting for something much, much better, which is a constant temperature, something that will actually continue to hold as we scale n to infinity. Scale n to be really, really big, take our systems to have many, many bodies. OK, to show how we get there, I'm going to first of all discuss a proof for why this perturbation thing is separable. So this will give you some kind of flavor of the arguments that we're looking at in this. It will give you some of the flavor of the arguments that are in our paper. OK. So how do I prove that identity plus a perturbation is separable? I'm first going to show that if I take the identity and add some Pauli, it's going to be separable. So here, this Pauli is a tensor product of individual Paulis. The proof is an algorithm. So I'm going to take psi to be a uniformly random +1 eigenvector of P. This is a random, I guess, stabilizer state corresponding to a +1 eigenvector of P. If I do this, then the corresponding density matrix of psi is going to be proportional to identity plus p. Right? Sort of, you're imagining that p has all these +1 and -1 eigenvectors. And then when you add identity, you're killing all your -1 eigenvectors, and you're only getting +1 eigenvectors. So you're just like a distribution over +1 eigenvectors. And so that's why your expectation is identity plus p. And also, your psi, you were choosing it to be a uniformly random eigenvector. And so it's just from the structure of p, this is going to be a product state. Right? It's going to be your tensor product of stabilizer states for every particular paly. And so we're expressing identity plus p as an expectation over product states, and therefore it's separable. So that's the proof. OK, now we're going to use this lemma for our proof that identity plus a perturbation is separable. The way we do this is that we write y in its paly decomposition. So we express it as a linear combination where of these palys, writing it in the paly basis. And then what I'm going to do is I'm going to do the same thing, which is the same proof argument. I sample a uniformly random paly p. Then I define this random variable, which is like the identity plus some rescaled version of this p that I sampled. And you can see that if I look at the expectation of this thing over the random choice of p, then my matrix is identity plus y, an expectation. And so I've written it in terms of, I've written this identity plus y as an expectation of this particular kind of random variable. And this particular kind of random variable is separable if y is sufficiently small. So these coefficients are actually bounded by the operator norm of y. And so identity plus a constant times a paly is going to be separable if this constant is bounded by 1. And so this shows that if 4 to the n times operator norm of y is at most 1, then we have that this random matrix is separable. And so, if y is sufficiently small, we're able to write identity plus y as an expectation, as a expectation of over separable states, and so it's also separable. Okay. This should be like the most technical that this goes, so I'll take a second for it to sink in. Okay. So this is how we're able to give algorithms that sort of prove separability in the course of, constructing these algorithms. With this, we can actually go one step further. So what we just proved was that if I take the identity and add some perturbation, it's separable. But this perturbation is exponentially small. You can't expect me to really work with this. So what I'm going to use is some corollary, which is that what I can do is I can write identity plus y as the identity plus y on the support of y, tensor the rest. And so when I do this, I can then do the argument on identity plus y on the support of y and say that this thing is separable provided the operator norm of y is exponentially small in the support of y. Okay? And so this is giving me a lot more leeway because now if I know my perturbation is local, like it's only acting on a couple sites, then I can actually move a lot and still be fine, still be separable. So if I have an identity and I add this perturbation that's only on a couple of sites, then I'm still local and I'm still separable. And it turns out that you can say something slightly more general, which is extend this to quasi-local perturbations. So a quasi-local perturbation, I'm imagining local replaced with quasi-local, basically instead of just having it act on one site, it can act on all the sites, but sort of the strength decays with the support size, decays exponentially with the support size. And it turns out that these quasi-local perturbations are also separable. So in particular, you can show something that looks like this. Here, I'm labeling every sort of y with a sort of support size. And every yTB is going to have support size t, but the weight or the size of the t support things are exponentially decaying with t. And so it really does look like this sort of, it's large on single sites, but maybe very, very small on larger sets of sites. Okay. And now that we're here, we might be able to start building some intuition for why Gibbs states are unentangled. So now I'm going to discuss some more of like the proof details and sort of give the key tool and try to explain how our algorithm works. So as the intuition for why high temperature Gibbs states are separable, you can imagine that what Gibbs states are they're maximally mixed states. So they are like perturbations from infinite temperature. So they are more or less maximally mixed, but they do have some mild correlations, and the correlations are quasi-local. So nearby qubits are going to be somewhat correlated, like a small amount correlated, but distant qubits are really like, they don't care about each other at all. And so you can hope to execute this separability proof, these arguments that perturbation of identity is separable. You can hope to execute this sort of locally on some small subset of sites at a time. And when we're doing this, we're sort of allowing ourselves to perturb by a constant amount as opposed to the exponentially small amount that we were allowing for the sort of general argument that I mentioned before, the naive argument. Okay. So that's the intuition for why these things are separable. We prove separability by giving this algorithm. So as input, we take in a Hamiltonian and an inverse temperature. And for the output, we take this thing as input, and as output, we give a random separable state, or separable operator, sigma, whose expectation is e to the minus beta h. Okay? And so this proves that, if we can show that this algorithm actually works, then we've proved that e to the minus beta h is separable, because it's an expectation over separable operators. And therefore, rho, which is a rescaled version of e to the minus beta h, is also separable. So okay, also, for the record, I'm describing this as an algorithm. So for now, don't worry about the running time of this thing. So we're just giving some constructive way of building this, and I'll worry about the running time later. The core subroutine is going to be the act of sort of pinning a site. And what I mean by this is that we'll take as input like some Gibbs-like operators, think e to the minus beta h. And we're going to output some state which separates a particular site. So we're outputting some random operator whose expectation is still my input operator, x. And all of the outputs are sort of tensored sort of product structure across a particular site j. Okay? So it's going to look like my output is going to look like a Gibbs-like state on all of my sites except for j, which is going to be separated from my output, from the rest of the output. And just to explain like what you can do with this, so if we have our e to the minus beta h and we have this subroutine, then what running this algorithm is going to do is it's going to give you one of many possible outputs. But what these outputs are going to look like is they're going to look like some site, then here it's the first site, tensor product, some Gibbs-like state on the rest of the thing. And so what you can do is then my output is going to be some particular x prime from one of these choices. And we know that the expectation is going to be e to the minus beta h. Okay, what am I going to do? I'm going to run this subroutine again on all of the sites except for the one that I pinned. And this will give me more sample outputs, again satisfying these conditions. I'm going to get one particular one, this x double prime. And over the randomness of the algorithm, this x double prime is going to be equal to the x prime in expectation. And over the course of over the randomness of the previous step, we know that in expectation x prime is equal to e to the minus beta h. Okay, so throughout we're maintaining that over the course of the entire algorithm, over all of the times that we run our subroutine, the expectation is equal to e to the minus beta h. And so if we run like all of the times, if we run as many times as we want, eventually we'll get some site where we'll get some operator where all of the sites are pinned. And its expectation over the entire course of the algorithm is e to the minus beta h. And now this thing is separable, and we're happy. Okay. So this is why you end up needing this kind of subroutine, or we want this subroutine. To discuss a little bit more, I'm going to define these notations of this restricted Hamiltonian. So if I take a particular Hamiltonian, I can imagine restricting to only the terms that act on a particular site, and I'm going to call that h sub I. And I can also consider restricting to all the terms that are contained in a particular set, and I'm going to call that h superscript s. So for example, if I take my Ising model from before, then if I restrict to site 1, then I'm going to get things that sort of act on 1 and also the adjacent things. So I'm going to get these two terms here. And the h superscript, what's left is the terms that I don't have in h sub 1 is going to be h superscript 2 through n. So it's going to be all the states that only act on 2 through n. Okay. So with this, I can introduce our key tool, which is this propagation operator, or like a propagator. And it's this thing in blue, this e to the minus beta h, e to the beta h, where the second h is on a subsystem. Okay? And the way that you can think about it is that it is sort of giving you the correlations of a particular site with the rest of your Gibbs state. So in particular, if I take this operator and I apply it to a Gibbs state on a subsystem, I'm going to get the Gibbs state of the whole thing. So you can imagine, like, I have my Gibbs state, and what this propagator is doing is, like, it's sort of touching things that are nearby the state that I want to add, and it adds it, something like that. Okay. Now, if I look at what happens for classical Hamiltonians, then all of these terms commute. And so I can actually write it in terms of just as e to the minus beta of this difference of these two operators. This turns out to be equal to h sub 1. And so this propagation operator is indeed local. In general, for quantum Hamiltonians, you don't get this nice commuting property, but you can still write it in terms of this series expansion. And there's this particular recursion that it satisfies. And this recursion shows you that this thing is quasi-local. Okay? So the propagator is somehow like saying that site 1 really only cares about what's going on in sort of nearby sites. It doesn't really care about what's going on far away. And so I can return to like sort of the subroutine that we wanted to demonstrate. And I'll run through what goes on in the initial step where we have as our input e to the minus beta h, and we want to extract out one site. We want to pin one site. So what I do is I write e to the minus beta h in terms of e to the minus beta times this subsystem h. And to get from the subsystem to the full system, we have these propagation operators. So far I haven't really done anything. This is just algebra. And what's going on here is that I'm really writing it as a subsystem Hamiltonian, subsystem Gibbs state, with these propagation operators that add my final site, my first site. And this interior thing turns out to be separable because it's quasi-local. It's a quasi-local perturbation of the identity. And in particular, it's separable. And that makes us happy because then we can write it as this expectation over separable states. So in particular, we can write this separable thing as this expectation of over these x's, all of which are separable. And in fact, we want them to be product over the site 1 through the rest of the sites. And so this thing now is just something acting on one site. You can see that there's like this x1 that only acts on one site, and everything else acts on only 2 through n, like the rest of the system. And so we can factor out this x1 into its own part, and this is the thing that we output. This is the output of our subroutine. This pinned, we have this random variable where one site is pinned and the rest is some Gibbs-like state. And so this is basically how it goes in the first step. In the second step, things get a bit more complicated, but it follows the same principle. You can imagine I take this thing, now I look at this subsystem. So we've already separated out the first site. And so now we want to see what we can do with the rest of it. So I can imagine this is like the rest of my system now. And now I want to write this as a, again, this sort of subsystem, now 3 to n, where we're pinning site 2. And to pin site 2, we need to add these propagation operators, which sort of model the site 2's behavior on the rest of the system. OK, now this is identical to the site 1's thing, except now there's this x in the middle of our expression. And so now the question is this thing separable? Can we then extract site 3 and then continue? So this is a good question. And this leads us to the considerations that we need to actually execute this argument. So there's a couple things that are underspecified about the subroutine as I stated it here. The first one is like, what is this Gibbs-like thing here? So what is the kind of operator that I'm allowing myself to work on? What is the sort of potential argument that I'm taking? What turns out to be possible is that we can operate on these, we can sort of pin sites, provided that they look like this. So we can pin a site provided it looks like some Gibbs state on, except there's this perturbation of A. So where A is this like identity plus perturbed by some Pauli. And the amount that we perturb is exponentially small in the support size of P. So again, like A is like a quasi-local perturbation of the identity. And so we show that if our input looks like this, then we can output this x prime where we have one site pinned and the rest still satisfies this condition. OK? And because we're able to do this, we're able to basically maintain that as if our input satisfies this structure, then our output can satisfy the structure as well, and we can recurse. OK, so here it turns out that if I take my x, this sort of operator that I wasn't sure how to choose, and I say that, the input came from this Gibbs-like state, so it's identity plus some constant times p, then you can show that it's separable. And this is how you basically execute the argument. And when you show that it's separable, then the next step is to write it in terms of these product operators, where it's one site pinned and the rest is this identity plus constant times Pauli. So again, you're always making sure that your intermediate operators look like this identity plus constant times Pauli. OK. So the second consideration is how do we choose this site to be pinned? So this is something that I haven't really specified. So far looks like I've just been doing the first site, second site, and so on. And it turns out that the natural thing of just going in a line, just doing 1, 2, 3, 4, and so on, doesn't seem to work. Instead, what we do is we choose the site to pin adaptively. So in particular, what we choose it to be is we choose it to be a site which is currently in the perturbation. OK? So remember that we have this Gibbs-like state as our input. Then the site that we choose to pin is going to be a site in the support of P. And the reason why is that as we continue extracting sites and pinning sites, we introduce correlation. So imagine that like I choose a site, like I choose my first site. Then this introduces some correlation, right? It says like if I know that my first site is something, then that says something about the rest of my state. And this is modeled by this operator A. And it turns out that if you like just choose a site naively, you can increase this correlation and increase this C enough so that C exceeds 1. and therefore you ruin your separability. Right? If C exceeds 1, then your A is no longer even PSD. You're not a separable state. And so what turns out to be the right thing is to choose a site in the support, because when you pin, you increase your correlation. But if you pin a site that's in the support size decreases. And so you're still maintaining that the size of C is exponentially small in the support. Basically, this is like the potential argument showing that we can recurse our argument from the original Gibbs state. And it shows that we can't increase the correlation too much, otherwise we'll run out of sites and we'll have to, and we like totally pin everything before it gets to be non-separable. Okay, so that's the argument. Now I'm going to discuss sort of the general class of results that we get. First of all, the separability stuff, and then some simulation stuff. So what I stated was a proof of separability for high temperature Gibbs states of local Hamiltonians on lattices. The full class of things that we show on our paper hold that works for these Gibbs states are Hamiltonians, which are low intersection. And so in particular, they work for these systems where the graph is not a lattice, but an expander graph, say. Our argument also works for QDITs. You get sort of like dependencies you expect. And finally, because we are proving a constant bound on this critical temperature, this holds even in the thermodynamic limit. So you take n to infinity, and your critical temperature is still constant. And I didn't state it, but we have concrete bounds. So you could actually for your favorite choice of Hamiltonian, you could figure out the critical temperature. The bounds won't be that good. Probably you need a model-specific analysis if you want something better. But you can actually get constant if you want. OK. As for the original result, we can actually show something stronger than what we had before. So remember that what we had before was we gave as input our Hamiltonian and inverse temperature, and the output was this separable state whose expectation is e to the minus beta h. So something I will remark without proof is that this algorithm is efficient. This isn't obvious at first glance, but basically all of your intermediate operators are Pallies, and you can maintain all of the sort of what's going on at every step as just some series expansion of of these Pallies. And so you're never working with all of your series expansions, all of your algorithm processing. You never have to write down anything that's really big. And in fact, I think it's maybe almost linear. It's n log n or something. I mean, don't quote me on that, but it's actually efficient. And so it's also, so in particular, I can say something even stronger, actually, which is that I can make this state that I output a stabilizer product state. So, tensor product of 0, 1, plus minus, I minus I. And so then my output is going to be some scalar times a stabilizer product state whose expectation is e to the minus beta h. And you might expect that now what I can do is I can just prepare psi on a quantum computer, and over the expectation of the algorithm, I get the Gibbs state rho. But this turns out not to be true because this mu can change. So I'm sort of, because the mu's are different for every output, I'm sort of weighting the product states differently, and I'm not going to get the product state, or not going to get a simulation algorithm for the Gibbs state. But with some additional massaging, you can actually show that you can make this scalar be the same for all outputs. And so this gives a state preparation algorithm, because then what you can do is then I can actually prepare psi. And then over the expectation of the algorithm, I get my Gibbs state rho beta. And this gives us a state preparation algorithm for high temperature. And I'm going to note that there's a concurrent work, which is going to be given in today, later this afternoon, which gives a similar result through completely different techniques, Lindblad evolutions. So you should check that one out. OK. And finally, we observed that this algorithm that we gave is basically classical. So this algorithm is classical, and it outputs a description, a classical description of a stabilizer product state. And so if we wanted to run if we wanted to know anything about our output state, we could just run it classically. Compute observables, measure in the computational basis, and so on. And so this gives us classical simulability of these Gibbs states at high temperature. So this was more or less known. There are prior works that are able to compute observables and measure and so on for these high temperature Gibbs states. Our work is sort of a generalization, sort of unification, gives a broad reason why you get this simulability in the classical setting. Okay. So finally, I'll discuss some takeaways. Our work shows this sudden death of thermal entanglement for qubit systems. And furthermore, we show that these high temperature Gibbs states are classically simulable. So some frequently asked questions that I get in regards to this. The first one is this sudden death of thermal entanglement hitting 0 at a temperature, is this a phase transition? And I'm not a physicist, so I maybe am not qualified to answer. But my feeling is that as right now, we're not calling it a phase transition. Just because it doesn't seem obvious to us that this lack of separability really actually leads to, it's not like a new phase of matter if something is separable in some sense. Like maybe just because the separability doesn't actually have this very strong operational definition. So even though it does seem like our entanglement measure is non-analytic at a point, which is sort of what you look for phase transitions, this seems like it's not really clear. Secondly, you might ask about other models. Is it true? Is this sort of message true? It turns out that in certain kinds of reasonable models, you don't see heat-destroying entanglement. In fact, you can get up to like very high or infinite temperature and still be an entangled state. All of these examples are examples where you have some symmetry in your system. So you imagine like I have a state that's very mixed, but I have to enforce a symmetry. So it's like mixed mixed except for this symmetry. And so our work sort of suggests that maybe the right message is that like heat is destroying entanglement only if you don't have symmetry. Okay. And finally, we have this question about like, okay, we proved classical simulability. What does it say about Gibbs sampling? I was going to describe some like possible worlds for quantum advantage for Gibbs sampling here, but I think we don't really know anything. Basically, for the general task of Gibbs sampling, all that we know is that it's NP hard below a certain temperature, and that is classically simulable above a certain temperature. And in the middle, we don't really know what's going on. It's not even clear that separability plays a role here. The separability temperature could be like, I guess, anywhere in this line that I drew here. It could be on the right of classically simulable. It could be on the left of NP hard. I'm not really sure. But basically, it is true that sort of if you want general quantum advantage, you're really narrowing down to this band of like between classically simulable and NP hard. And so this suggests that maybe if you want to look for like a strong case for quantum advantage, like a really strong case, then you might have to go to like specific models and not just general Gibbs sampling. As for some future directions, maybe one of the most obvious ones is to actually pin down what this critical temperature for entanglement is, maybe for a particular model. So here's what our current bound looks like. We show that entanglement below 1/100 times the degree of the Hamiltonian times the locality squared. We don't have any corresponding upper bounds. Yeah, so it's interesting to try to figure out, can we pinpoint it exactly? This would be like sort of in the spirit of the statistical mechanics kind of perspective on this. Secondly, we have this separability algorithm that's able to, this like fast separability algorithm, which outputs the stabilizer state whose expectation is the Gibbs state. Can we actually run this for models of interest? And is this a way to like computationally investigate separability of these states? Or can we use it to even do other things like estimate observables and so on? I'm not really sure. Finally, we do have this new decomposition of high temperature Gibbs states, which show that they're sort of morally classical. And can we use this decomposition to port classical strategies for proving correlations of quantum systems results to this quantum setting and prove new things here? Because right now, even for high temperature Gibbs states, we don't actually have that many strong techniques, or we don't have techniques as nice as the classical literature for this kind of stuff. And so it'd be nice to potentially try to port things from classical to quantum here. Okay, thanks.
All right, thanks for the great talk. I think we have time for a few questions. I see one in the back.
Test. Thanks for the stellar talk. That was absolutely wonderful. Much of what you say works for qubit systems, but you also mentioned that it should also apply to qubit systems.
Yeah.
So my question is, like, how does the critical temperature for separability depend on the local dimension? And could you also think of like similar statements for families of states with infinite local dimension, like say Gaussian states, where we would also expect a critical temperature in a similar sense?
That is a great question. So I can tell you what the exact statement is for a qubit system, the critical temperature does not depend on the local dimension, but it does depend on, but only for these Hamiltonians that you can write as like a particular term is like an operator, tensor, another operator, tensor, another operator. So like sort of maybe like the simple building blocks. You just need to write your Hamiltonian in terms of these building blocks, which are product operators. And then once you do that, then it doesn't depend on the local dimension. But I mean, decomposing this could require some local dimension payment, but I don't think that's like that's the only thing that you pay. As for infinite dimensional, I think I'm not really sure. I think it's possible, but I'm not sure. Or sorry, infinite dimension, yeah.
Great. Another question back there. Oh.
Sorry, a very brief follow-up to that previous question then is like, how does that generalize to fermionic systems?
I think the natural analog would be that fermionic systems can be written as linear combinations of Gaussian states. I'm not really sure about entanglement. So I know that there's a group that has work on this. So if you want to know more, you can talk to me, and I'll point you to them.
I'm also slightly curious because right, so you mentioned like the exact like critical temperature that you proved. Like, so if you just like say we are like very, very careful when we are like massaging all the constants, will that only just like make that 1/100 that 100 better and like still have like the same form? That's what your expectation is?
Right, so what do okay, my guess for the optimal temperature would be something like potentially like 1/degree times locality. Right now we have 1/degree times locality squared, and I'm not sure if the locality, that second locality can be removed. But I am not sure. Yeah, I don't, like, I think the idea would be to do it to get the constants improved enough so that it sort of matches other kinds of critical temperatures, and I'm not really sure where it'll stand relative to the other temperatures, if that makes sense.
Thank you so much.
Right, is there another question?
Hi.
Yeah.
Yes, thanks for the nice talk. I was wondering if you can, so in your work you have this critical temperature, and there's also this previous work of Haro, Miraban, and Suleymanifar, where they consider a high temperature series expansion and give a classical algorithm that works up to a critical temperature that is defined by the complex zeros of the partition function as a function of complex temperature. Do you know if those critical temperatures where these two algorithms succeed coincide, or if they're different?
I would expect that. So the simulation algorithm is actually bottlenecked by the separability argument. And so the separability argument is actually the worst one. And so the actual, like, My guess would be that the critical temperature for separability is, let me see the directions. Maybe it could be worse than the critical temperature for simulability. Yeah, it could be that this sort of algorithm will never achieve it as good as the one that you mentioned, this with the complex zeros. But I'm not entirely sure. It could be that all of the critical temperatures are the same, and then things would be nice. But I'm not sure.
Thanks.
All right, one more question? Yeah.
Yeah, so thanks for the awesome talk. I'm curious, have you started to think about what the implications of your work would be for room temperature fault-tolerant quantum computing, or its implications for error correction?
I don't know if it has any implications beyond like what we sort of already know, which is that above a particular temperature, things are mostly classical. So if you have this physics intuition already, then this doesn't say much more than that, I guess. Yeah, that's what I would say.
All right, we're going to take one more question.
Yeah, thank you for the next talk. Yeah, you mentioned that if beta is substantially large, then in the beginning you sketched a very simple proof for showing that if beta is very, very large, then there's a very easy way to see that your Gibbs state is separable. And then you managed to get it down to just entirely constant. So I was curious if there's any techniques in your paper that just simplify a lot if you're happy with beta being, like log n or depending weakly on the system size.
Yeah, so that's a great question. So I sketched out the statement that quasi-local perturbations of the identity are separable. So if you imagine taking your beta to be like 1 over n, then I can just Taylor series out my e to the beta h is like sort of 1 plus, or identity plus beta h or something. And that's like morally what it is. And this thing for beta small enough, like a polynomial in n, this thing is a quasi-local perturbation of the identity. And so I get separability from that argument of, let's say, 1 over poly n. Yeah, that's the, I guess, intermediate setting. Yeah.
All right, we'd like our next speakers to come backstage to get set up. And in the meantime, we'll thank Ewin again for a great talk. Thanks.